Have you ever wondered why nickel superalloys, known for their exceptional high-temperature performance, are still prone to cracking in additive manufacturing? If you're in charge of ensuring high-quality metal parts, understanding this critical issue can save you time, money, and a lot of headaches. In today's video, we're diving deep into the root causes and common types of cracking in nickel superalloys during additive manufacturing and how you can better manage these challenges. Hello, and welcome to this essential discussion on a pressing issue in metal additive manufacturing: the cracking susceptibility of nickel superalloys. This is especially critical for technical managers and engineers who need to deliver reliable, high-performance parts. Let's explore what causes these cracks and the different types of cracking that frequently occur in the additive manufacturing of nickel superalloys. Additive manufacturing methods like laser powder bed fusion, LPBF, and electron beam melting, EBM, involve rapid heating and cooling cycles. These cycles create steep thermal gradients within the material, generating high levels of residual stress. When this stress exceeds the yield strength of the nickel superalloy, it releases in the form of cracks. The component's size and shape significantly impact the magnitude and distribution of these residual stresses. Nickel superalloys, particularly those strengthened by gamma-prime precipitates, have a very narrow solidification range. This means the window between fully molten and fully solid states is very small. Combined with rapid cooling rates in additive manufacturing, there's minimal time for liquid metal to flow and compensate for shrinkage, which leads to solidification cracking. Elements like carbon, C, zirconium, Zr, and boron B, often found in nickel superalloys, can aggravate cracking issues. These elements tend to widen the solidification temperature range, trapping liquid metal between solidifying structures longer. This residual liquid becomes highly susceptible to cracking under thermal stress. Understanding the different types of cracks is crucial for developing targeted strategies to prevent them. This type occurs during the solidification process and is primarily driven by high thermal gradients, rapid cooling, and shrinkage stresses. Solidification cracks generally form along grain boundaries and interdendritic regions where residual liquid persists during the final stages of solidification. Liquation cracks form at temperatures below the solidus, often during cooling or post-processing heat treatments. They occur when a low melting point phase forms along grain boundaries and melts due to localized heating, compromising grain boundary cohesion and leading to cracking. DDC is a form of strain-age cracking often observed in age-hardenable alloys, like Inconel 718. It typically occurs during post-weld heat treatments or stress relief cycles when the material temporarily loses ductility. The mechanisms behind DDC are complex, but generally involve the formation of brittle phases and strain concentration at grain boundaries. Oxide-induced cracking is caused by the presence of oxides on powder particles or within the build environment. These oxides can serve as stress concentrators, promoting crack initiation. During the melting and solidification processes, some oxides may not fully melt, creating weak points that facilitate crack propagation. Understanding these cracking mechanisms is key to developing effective mitigation strategies for nickel superalloys in additive manufacturing. Stay tuned for our next video, where we'll cover practical solutions and best practices to minimize cracking and improve the quality of your metal parts. If you found this video helpful, please like, subscribe, and hit the notification bell so you don't miss out on future updates. And don't forget to share this video with colleagues who are also navigating the complexities of additive manufacturing. Thank you for watching and see you in the next video.